Today we're going to extend our talk about polynomials to a new type of function called a rational function. This section starts on page 221 in your text. So what is a rational function? Okay, so it's no longer a polynomial like what we've been dealing with, but we'll see a lot of the related topics, intercepts, zeros, thinking about what happens sort of at the ends of the graph. That will come up here as well. So a rational function is one with the form where you have a fraction. Okay, so rational comes from the word ratio. Ratio means fraction. So we're going to have a fraction of two different functions. N for numerator, D for denominator, where both of N and D are polynomials. Okay, so we're building it up, right? We've been talking about polynomials for the past couple of lessons, and now we're going to do something with the polynomials, but that changes the structure, okay? So we'll look a little bit at what's changing, but how we can still relate it to things we've covered already. So as an example, let's start with one that you've already done. You've graphed, discussed domain and range for this function, 1 over x. You did this for the translations worksheet. And as a review, here's what that graph looked like. And in this instance, we also discussed the domain. Okay, so remember what domain was. Domain would be what x values are we allowed to plug in, right? Domain always refers to the x values. So we can either look at this algebraically and say, oh, x cannot be 0. Or we can look at the visual and the graph because it's right here. Think again about sort of squishing this graph into the x-axis. What gets covered and what gets missed? Well, everything gets covered except the origin. There's no part of the graph touching at the origin if I were to squish this down. So x can't be 0, or if you prefer the interval notation, that means we go up to 0, but we skip over it in the following way. So negative infinity to 0, union 0 to infinity. The range is similar because we have some nice symmetry happening here, but range refers to y value. So I would say y can't be 0, but the same interval will apply, and I would be doing my squishing into the y-axis. So what gets covered is negative infinity to 0, don't include 0, and then everything from 0 and up above. Okay, so we have this sort of idea, and we're going to talk a little bit about what's sort of going on here. Like, why do we get this sort of visual happening at 0? Okay, where my line, my graph is going to get really close to 0, but never actually touch it. And same thing down here, get really close to 0, never actually touch it. And we have similar things happening as we look at what's going to the right. We're getting really, really close to the x-axis, never touching it. Really, really close to the x-axis over here, never actually touching it. So we're approaching some sort of a limit or a line happening throughout. We're going to refine that idea a little bit more. Before we do, I want to look at another example of the graph of a rational function. Let's call this one g of x. And this will be x squared minus 4 divided by x minus 2. Okay, so we see numerator is a polynomial. I could graph that. It would be a parabola that's been translated down 4 units. Denominator is a line with slope 1 and y-intercept negative 2. So I could graph them each separately, but what happens when I try to divide them? Okay, so in this instance, I want to just remind us of something we're always going to do. We're always going to simplify first. Okay, so this numerator factors. It factors into the quantity x minus 2 times the quantity x plus 2. It's a difference of squares factor. Denominator is as simple as it can get. It's x minus 2. But from this instance, I see, oh, I've got a common factor, which I can proceed to cancel. So I'm left with a function that is actually just x plus 2 with a small caveat. So I've got a comma there because of this domain issue. Because I cannot plug in any value that would cause division by 0, I have this special caveat we have to consider here. Looking back at the original, if x were to be 2, 2 minus 2 would be 0. That's still illegal in all of mathematics. This sort of division by 0 can't be undone. It's like a black hole. It sucks you in. You can't get back out. X can never be 2. Okay, the algebra of how we're arriving at that is just, again, from the algebra of the domain. X minus 2 can't be 0. Can't divide by 0. That means X can't be 2. Okay? So reviewing some of these previous concepts. So if it weren't for that caveat, this would be a pretty simple graph. This is just y equals mx plus b. M is 1, b is 2. So I'm going to start by graphing what I know, then I'm going to come back to this weirdness happening right there. So if the y-intercept is positive 2, put a dot at the y-axis point of 2, and then my slope is 1. So that means I can go down 1, left 1, down 1, left 1, or I can go up 1, right 1, up 1, right 1. And just play connect the dots. All right, but when I get to this point of 2, which I'm at right now on my graph, I don't want to include it. I want to skip over it. So we've done this sort of skipping over idea before. Think about what the number line looked like for this interval. When you skip over something, an open circle appears. But the graph still continues beyond that. So I have this line with a hole in it, with a gap, okay? So I get the graph of a line with a hole at x equals 2. I don't want to include 2. 2 is eliminated, okay? Represent that graphically with a hole. If x is 2 and I need the y value, okay, if x is 2 and I need the y value, maybe I have to label it, maybe I have to input it into WebAssign, maybe I just need more information for my graph. Go back up here. All right, look at our simplified version. If I make x equal to 2, 1 times 2 plus 2, my y value is 4. So I can always plug in x and get out y if I need to label the coordinates of that missing piece of the graph, okay? So we have sort of some entry-level rational functions happening here where we've graphed this before, we've graphed lines before, this is just line with a hole, okay? But things are going to get a little bit more complicated when we kind of bring these two topics together. This sort of approaching a line and the possibility of holes and extra simplification, all right? All right, so we're going to talk about asymptotes. Maybe you were already thinking of this word when you saw things on the graph that were approaching lines, but really an asymptote is just going to be, for our purposes, it's going to be a line that the graph approaches. Gets close to, may or may not touch, but it's some sort of a limit. I'm going to get really, really close to it. So I like to liken this to if you have a younger sibling, or maybe you were a younger sibling, and on long car trips, you know, inevitably it was always the younger one that would start to play the game of like getting closer and closer to the older sibling and saying, well, I'm not touching you, well, I'm not touching you, well, I'm not touching you, but still just getting annoyingly close. That's an asymptote. We're going to get annoyingly close to some lines. We may or may not end up touching the lines, but knowing those sort of limits, that annoyingly close part, will help us figure out what the graph looks like. Okay? So, vertical asymptotes. So we have got vertical and horizontal that we're going to discuss. So some sort of a vertical line that the graph will get close to. Okay, vertical asymptotes come from uncanceled factors in the denominator of our rational function. Okay, from the bottom part. All right, horizontal asymptotes that's not as obvious, okay? So why is a vertical asymptote coming from an uncanceled term in the denominator? Well, if it doesn't cancel, I can't plug it into the function because I can't have the division by 0 happening. So if I can't plug it into the function, I'm going to get really close to it, but I'm never going to actually touch that specific value, okay? So this is coming from the fact that we cannot divide by 0. Now, why would my graph ever approach something in the horizontal direction? Well, this comes from looking at some end behavior. What happens as x gets really, really big, positive, or perhaps really, really big, negative, okay? At the end of the next discussion, we'll have sort of some rules to go off of, but I don't want to just give you those rules without giving you some background, some context, because that often helps us remember things, is if we can connect it to previous information, rather than just having to memorize something brand new. So there's going to be 3 particular cases, so we're going to run through 3 examples, and then form the rules for the horizontal asymptote, okay? So the first possibility might take the form, right, looking at a specific example first, like the following. Okay, so I've got 3x minus 1 over x squared minus x minus 6. I want to look at what happens as x gets really, really big, okay? So in order to do this, I'm going to invoke a little bit of algebra. I'm going to try to simplify this, and just like what I can do with numbers, I can do with a rational function. I'm going to divide the top and bottom by the same number, okay? But really not a number, but instead a expression. So whatever I do to the top, I do to the bottom to keep everything still equal. If I just do it to one part, I don't have equality anymore. So for 3x minus 1, I'm going to divide by x squared. And for x squared minus x minus 6, I have to do the exact same thing, otherwise I lose equality. Okay. You might be wondering, well, why am I doing that? Let me kind of come back to that at the end and just follow the algebra through. And we're hoping that this can simplify what we need to look for. What's happening is x gets really big, okay? So the simplification that I can do here is take every term and divide it by the x squared. If you can do quicker simplification, feel free to. I want to document my entire thought process here on the board, okay? It's kind of like I have a common denominator, so I can break the fraction up into 2 individual fractions. Here there were 3 fractions, break it up into 3 little guys here, all right? So 3x over x squared, I can simplify to 3 over x. I cannot simplify the other term. Minus 1 over x squared has to stay. In the denominator, x squared over x squared is 1, anything divided by itself. X over x squared is a 1 over x, and I can't simplify the last one. Okay, this doesn't look better, right? Look at where we started, look at where we are. It looks worse. But remember, I want x to grow really, really big. Really, really, really big, okay? So if I think about x is getting huge, infinitely big. If I have 3 and I divide it into 5 parts, okay, that's not very big. But if I have 3 and I divide it into 10 parts, it's a little bit smaller. 3 divided into 100 parts, smaller still. 3 divided into 1,000 parts, smaller still. 3 divided into 1,000,000 parts. I'm getting smaller and smaller little individual pieces as I divide by a big number, okay? So what I'm trying to say here is if we divide by something big, the fraction gets small. Let me include that in words here. Division by a big number, like infinitely big, results in a small number. That's how I'm going to simplify this. If I'm dividing by x and x is big, that's so small I'm going to call it 0. If I divide by x squared and x is big, this is so small I'm going to call it 0. In the denominator, oh, I've got more division by big things, more division by big things. So I'm left with 0 minus 0 in the numerator, which is 0, and then 1 minus 0 minus 0, which is just 1 in the denominator. 0 divided by a number, that's okay to have 0 in the top, is 0. So at the end of this result, okay, this is telling me that we have a horizontal asymptote. I'm going to abbreviate, just calling it HA for horizontal asymptote, at y equals 0. What was happening at the end? At the end, when x was really, really big, I was left with nothing at all. Horizontal asymptote at 0. Okay. I'm going to run through two very similar constructions here, but I may run through them a little bit quicker because I've kind of explained this guiding principle and how the division part works, okay? All right, so for part B, I want to look at a different function. Let's call it G, give it a different name, and it'll be set up. It's just a specific example that will help us form some rules in a moment. All right, I'm going to divide everything by x squared. So that means first term gets divided by x squared. Second term gets divided by x squared. Same thing in the denominator, dividing everybody by x squared. Simplifying. 5 plus 1 over x squared divided by 3 minus 4x squared. X is getting big. Divided by big things results in small things. That's 0. So small it's practically 0. So I'm left with 5/3. So I get a horizontal asymptote that's 5/3. Okay. Again, I'm doing these specific examples and I'm hoping to generalize later. So think about where 5/3 might have been coming from in the original problem. I mean, maybe we could skip these intermediate steps, okay? I'm going to leave that one up there and go to C, okay? So part C. Suppose it looks like 2x to the 4th minus 3x squared plus 5 over x squared plus 1. I'm just going to divide every term by x squared, simplifying it as I go. So if I divide by x squared, I'll have a 2x squared minus 3 plus 5 over x squared. Can't simplify that last guy. Divide by x squared, I'll have a 1 plus 1 over x squared. Division by big things results in small things. So small it's practically 0. So small it's practically 0. Simplified version looks like 2x squared minus 3. 1 plus 0 is 1. There is no denominator. You can write over 1 or not. Feels a little redundant. It's okay to have it. It's not necessary. Alright, so as x gets really, really big, I'm not dividing anymore by x. X is in the top, not the bottom. So if x is huge and I square it, and then multiply it by 2, it's still big. Subtracting 3 isn't going to take away from its bigness. It's still going to be big. So this ends up being gigantic, all right? Which means I'm going to have no horizontal asymptote. I'm not approaching anything. I'm growing without limit, without bound. I'm going off to infinity, okay? So I don't have all 3 up here anymore. Let me just write that first original one, and we can kind of compare all 3 and hopefully form some sort of a rule of thumb that'll cut down on our computation. Okay, so the first one was the original f function, 3x minus 1 over x squared minus x minus 6. And this result had a horizontal asymptote at 0. Okay, so trying to make some generalizations here. Okay, so our rules are going to tell us the following. Okay, this is all for horizontal asymptotes. We're always going to look at the degree of the numerator function and compare it to the degree of the denominator function, top and bottom. So remember, degree was highest power of x. So in this case, which power of x is higher? The bottom. So I'm in the case where the denominator degree is bigger. And my end result was a horizontal asymptote at 0. So my graph is going to get real close to the horizontal line of y equals 0. Let me jump down here. I will do this one next. Okay, usually I save this one for last because it's the more complicated one to say, but it is the second example we did. Okay, so in the case where the degrees are the same, highest power 2, also highest power of 2. When they are exactly equal, then the horizontal asymptote is ratio of leading coefficients. All right, complicated to say, not complicated to show. 5/3 is the ratio. Ratio means fraction. Come back to the original. 5/3. 5/3 is the ratio of the leading coefficients. Done. All right, last case was when the numerator's degree was bigger than the denominator's degree. 4 versus 2. Numerator is dominating that. In this instance, we have no horizontal asymptote. We're not going to approach anything in the horizontal direction. Think about this guy. He was 2 versus 1. He's in this third case. There was no horizontal asymptote. I'm not approaching any number in the horizontal. I'm going off to infinity. Going off to infinity. Okay? All right. So we've discussed sort of all these rules, but we really need to end the video with an example. It's going to be lengthy. Okay, so if you're taking notes, maybe turn the page, start a fresh page of notes. I'm going to try to provide a lot of detail in this example because it is the first one that we're going to do very thoroughly. Okay, so I need an entire board's worth of space, and you may need an entire page of notes. So we're going to take all the parts that we've talked about, the wholes, the simplifying, the asymptotes. We're also going to take ideas from previous topics, intercepts, and build a graph. All right, so what are we graphing? All right, so here's my function that I want to sketch. 3x squared plus x minus 4 over 2x squared minus 7x plus 5. Okay, I'm going to have numerous steps, building a lot of information, and then at the end I will have a visual, a sketch of what this looks like. Okay, trying to bring together all of these sort of disconnected topics in this one problem. Step 1, always factor and simplify first. Maybe things cancel out, like that line problem. Maybe we'll get lucky and this will actually be quite simple. Okay, I'm going to factor the top. If you do not need this review of factoring, just factor it on your own, pause the video, factor it on your own, and then zoom ahead to check your factors. If you need this, please follow it, okay? Multiply the first and the last numbers. You get negative 12. I need to break negative 12 into factors that add to 1, the coefficient of the middle term. So 4 and negative 3 add to 1. That's not always going to be these numbers here, okay? Those are just the factors that add to positive 1. Notice it's actually not these factors, it's the reverse sign. That's just a coincidence. That's not a rule. All right, so I've recreated the middle term as the sum of 4x and negative 3x. I still have equality though. From there, I want to factor by grouping. So looking at these first two terms, they share an x and nothing else. Looking at the last two terms, they share a negative, and that's it. So I'm going to factor out a negative 1. That's going to turn the terms positive. Now I have, let me double underline, a match. That should always happen when we're doing this factoring by grouping. So I can factor out what matches, and then what didn't get underlined, x and minus 1, forms the other factor. So I have factored the numerator into 3x plus 4 over x minus 1. Okay, again, try maybe the denominator on your own. I will go through it in the video, but feel free to zoom ahead if you are okay with your factoring. Just make sure you check that your factors match mine, okay? So I'm going to start with the denominator's factors. Notice you can also do guess and check. I used to do that quite a bit, but I like how this will definitely give me the right answer without having to spend multiple attempts on guesses, okay? Multiply the first and the last, 10. Factors of 10 that add to negative 7. Negative 2 and negative 5 do the trick. Add them together, I get negative 7. Multiply them, I get positive 10. Again, it is just a coincidence that 2 and 5 also were the first and last terms. That will not always be the case. Don't use that shortcut. It won't work all the time. Pair together the first two. They share a 2x. Write down what's left over. X minus 1. Pair together the next two. They share a 5, but I always like to have that first coefficient be positive, so I'm actually going to factor out a negative 5. That's going to change the first term to being a positive x, change the second term to being a negative 1. Now that I see a common factor being shared, factor that out. What didn't get underlined is the second factor. All right, so I have my denominator. All right, factored. Now is the fun part. I get to simplify. All right, so cross out, right? A common factor in the top and in the bottom. It's gone. So my end result, I have a simplified function now. It's not a line, it's not that simple, but it is simpler than what we started with. With a caveat, yet again, I canceled something. We've done this before, just once before, so I'm putting the reminder in here. I can't accidentally divide by 0. So x minus 1 cannot be 0. X cannot be 1. So I'm going to have a hole in this graph as well. Okay? I need to erase some of my factoring work. That's up here now. Of course, you can pause the video if you need it. But I'll leave the steps up here so that we catalog everything we need to do for future problems. Step 2, identify any holes. Okay, already mentioned. I had to skip over x equals 1. I'm skipping it. X can't be 1. So 1 is the x value of a hole. And then I need to fill in the y value. So I'm just going to put a question mark in there for now. Whenever I need a y value, I just plug x into the function. I could plug him in here, but I'm going to choose to plug him into the most simplified version I've got, which is this one. We worked hard to factor and simplify. Let's use it. So if x is 0, y would be, if x is 1, y would be 3 plus 4, 7, 2 minus 5, negative 3. That's my hole. I need the x and the y value for full credit, for WebAssign, for tests, x and y. Okay, so that's my step 2. Step 3, let's talk about x-intercepts, which we have mentioned before, which we used for polynomials, which we sometimes call zeros. They occur when y equals 0. Okay, so I'm going to set this whole function equal to 0. Y is the output. Not just the 0 here, but I'm actually going to set it equal to the simplified version, right? I can use any version I want. Let's use the most simple version we've got in front of us, okay, which is the one after we factored and canceled. Okay, solving this, I could multiply both sides by the denominator. That's not hard work to do. 0 is powerful. He sucks up this denominator. 0 times anything is 0. So on the right-hand side, the denominator's gone. I multiply both sides by it. It's canceled. Then subtract 4, divide by 3. All right, there's my x-intercept. My y-intercept is next. Y-intercepts occur when x is 0. So again, I can plug 0 in for x at any step. Let's use the simplified version. It's right there in front of us. So if I make all the x's 0, I'll have 3 times 0 plus 4, I get 4. 2 times 0 minus 5, I get negative 5. And that's my y-intercept. Okay, so I'm building a lot of this stuff from the graphs that we've talked about already. New stuff. Let's talk about vertical asymptotes. Abbreviating them the same way I was abbreviating horizontal, just with a V instead of an H. Vertical asymptotes came from uncancelled denominator terms. Let me record that again. Uncancelled factors of the denominator, the D part, the bottom. So 2x minus 5. That didn't cancel. If I set it equal to 0, right, because I can't really plug that into the function, then I'd have division by 0, and solve for x, I get a vertical line of 5 halves. That's going to become my vertical asymptote. 6, the horizontal asymptote. This is where we need to look at degrees. For what case are we in? Okay, well, I'm in the case where the degrees are equal, 2 and 2. So I take the ratio of the leading coefficients, and I get a horizontal asymptote that is y equals 3 halves. Okay, a lot of information that we're going to use to construct the graph. There is going to be a step 7, okay, which we don't always need. So let me show you where we're at right now, okay? What things can I plot for sure? Well, I'm going to start by plotting these asymptotes, okay, because maybe we haven't seen how they could look. They're going to be dashed lines on a graph. So x equals 5 halves, so that's 2.5. That one's all dried out. 1, 2, 3, 2.5. So I'm going to dash a vertical line at 5 halves. Then I'm going to dash a horizontal line at 3 halves. That's 1.5. Okay, so my graph is going to get really close to these lines, may not actually touch them, but these lines are going to sort of form boundaries in the shape of the graph. Okay, other things that I can start plotting. I'm going to come back to the whole. Let me start with intercepts. -4/3. Okay, so, just estimating, it's just a sketch. -4/3, maybe there's a dot right there. Y equals -4/5. That's like -0.8, so maybe there's a dot there. All right, well, let me go back to where the hole was 1, and then that's a little over -2. So +1, but a little over -2. Open circle, we called it a hole. Okay, so I need to connect these dots here, but I have these boundaries that are the dashed lines. So let's think about how that has to look. Gotta look like this and like this. So notice how my graph is getting really close to this horizontal line, but the horizontal line is sort of bounding it. I'm not really crossing that horizontal line. Same thing here with this vertical line, a little bit harder to see maybe, but I need to show that I'm getting close to the vertical asymptote, never really touching it. It's serving as sort of a boundary, a limit to my function. All right, so we're up to that step 7 that I kind of alluded to. Step 7 is additional points as needed. And I need them here. Okay, here's why I need them. I know what's going on to the left of my vertical line. I have no graph, nothing happening to the right. I haven't graphed anything over there. The information provided just didn't give me anything, maybe a little unlucky, maybe just the way it panned out. So for an additional point, I had to choose something that lives to the right of this line, okay? So let's choose 3, okay? 3 lives to the right of that line. This is 2.5, so let's try 3. I'm going back to just plotting points, right? Whenever I'm in doubt, I can just plot points and try to construct the graph. So again, I can plug 3 in anywhere. Let's plug it into the simplified version. So if x is 3, y is 3 times 3 is 9. 9 plus 4 is 13. 3 times 2 is 6. 6 minus 5 is 1. So here's an additional point. My graph goes through 3, 13. So 3, going to be kind of off the charts here. Let me just pretend that that's 13. But knowing that one dot is enough. Knowing that one dot, because I have these asymptotes, these barriers, these limits, I got to get close to both of these lines. So that is the shape. Oh, I realized I did that one in blue and this one in black. So let me go over one more time and say that the actual graph is in blue. The function is graphed in blue. The asymptotes are just in the black dash. They're forming my barriers, okay? But it is the blue that is the graph of G, okay? I realize there's a lot of steps here, and you're going to get practice on each particular component. We've already practiced x-intercepts and y-intercepts. Factoring we've already practiced as well. So the new stuff is just the asymptotes, the whole, and then being able to connect the dots in the right ways, okay? Let me know if there's questions on the video. Just post it to the comments so I can put answers up for